Hi everyone, and welcome to the 22nd and also the final TIA Centre seminar of the academic year. So my name is Adam Shepherd, and I'm a postdoc here at the TIA Centre, and it's nice to see that we've got some new faces, of course, in our seminars. And for those of you that are new to our seminars, we aim to invite researchers from across the globe to present new and exciting work. So today I'm delighted to introduce Dr. Sajid Javed. Sajid is an assistant professor of computer vision at Khalifa University of Science and Technology. He's affiliated with KUKAS, or Khalifa University Centre of Autonomous Robotic Systems, and the University of Warwick. Dr. Sajid received his PhD in computer science and engineering from the Kyungpook National University, Korea. Previously has worked as a research fellow at Warwick, and he now leads the computer vision group in KUKAS, where his current research interests span the field of computer vision and computational pathology. And the title of Sajid's talk today is CPLIP, Zero-Shot Learning Histopathology with Comprehensive Vision Language Alignment. So Sajid, thank you again for joining us. It's really great to have you back at the centre, well, at least virtually, and presenting the new work. So when you're ready, feel free to start.
Thank you very much, first of all, Adam, for such a gentle introduction of mine. Secondly, would like to thanks TIA Lab, especially Professor Nasser Rajput for having me today in the TIA seminar series. So today I would like to talk about one of my, work recently, accepted in CVPR earlier this year, which is CPLIP, Comprehensive Pathology Language Image Pre-Training Model, which has shown a very strong, journalization capabilities across various histopathology data sets. So I would like to, first of all, it's always nice idea to acknowledge those co-authors who have contributed equally in this work. So this is a joint work between Khalifa University UAE and the University of Western Australia, and the Information Technology University, Pakistan. Together with my two postdocs and strong collaborator across Australia and Pakistan, we were successful to produce a CPLIP paper in CVPR earlier this year. So I would like to take a gentle introduction of, the PLIP model, which is one of the seminal work in the computational pathology in nature medicine. Then would like to, draw a motivation towards the comprehensive pathology language image pre-training model, which is basically our proposal, followed by, its basic components, the steps to reproduce the, textual description, the visual data, and conclusion and the future directions. So connecting histology images and textual descriptions nowadays is not a very innovative approach. In fact, there are a couple of papers which have been produced in the recent years. One of the seminal work is a PLIP model, the pathology language image pre-training, produced by Hong et al., the Stanford group in the recently Nature Medicine. The idea behind this PLIP model is a straightforward, similar to the PLIP approach. Given the histology images and the textual description, the idea here is to align the positive images with their corresponding textual description. And this is basically a one-to-one alignment where image is given, the textual description is given, and the idea here is to align them together using the contrastive pre-training objective loss function from image to text or the text to image pairs. Both loss functions are symmetric, so it depends on us if you would like to go from image to text or text to image. The idea here is to the positive pairs will be drawn closer together while the divergent one will be distance one. It means that the negative pairs will be ignored while the positive pairs will be considered. And they show a very strong, representation capabilities across various data sets. Well, if we apply the zero-shot evaluation using the PLIP model in the zero-shot setting, or what we call it as an inference, given the unlabeled histology image and a input text forms, an image, an H&E image of a tumor, adipose, lymphocyte, epithelium, or a couple of more classes you would like to add, the idea here is to align the textual description with the input histology image. This is what we call it as a zero-shot classification. So the classifier will work as follow. It will compute the embeddings from the textual description as well as from the image modality using the vision encoder and the textual encoder, and it will produce a set of probability values. So the higher probability will definitely correspond to the input textual prompt, which is basically an H&E image of a tumor. So PLIP model has shown a very strong zero-shot generalization capability across, various data sets such as Cather-Poland data set, PAN-MUT, DigiSpot, WSSS4 LOART. And it means that we can apply the PLIP model in any unseen data which we would want to classify or segment it. Why? It is a one-to-one alignment. One of the possible, disadvantage of previous vision language model in computational pathology is they are very straight away. Okay, they align one image to one textual description. For example, here is the I1, which is a histology image, and there is a D1, which is a textual description of this specific image, epithelium showing mild dysplasia. And contrastive pre-training loss is then, straight away trained on those kind of one-to-one alignment, I1 to D1, I2 to D2, I3 to D3, and etc. The problem here is they show poor zero-shot generalization capabilities if we, strike the contrastive loss function to align one image to one textual description. While one image may have, varying kind of textual description, we cannot restrict the pre-training contrastive loss function to only one kind of a textual description. So here our proposal is a many-to-many alignment, okay? The many-to-many alignment is basically motivated from the term comprehensiveness. The term comprehensive means complete. We cannot restrict our vision language model to align only one image with one textual description. In fact, there might be several, histology images which can be aligned to, several textual descriptions. So here the term comprehensive means you can align multiple images with multiple textual description. While the description is not the only clue, the pathologists, the expert pathologists are, looking to diagnose any kind of, cancer or grading the cancer. In fact, causes and symptoms can play a very vital role to train with your vision language model. Here, the causes and symptoms can further be enforced within the description with each histology image to further, make stronger the generalization capabilities of your computational pathology model. The advantages here are, threefold. You will get more detailed description, you will get better zero-shot capabilities, you will get better generalization capabilities across, various data set. And we have shown this in this work that it has outperformed many, vision language modeling in the literature. Fine. So when we talk about the comprehensiveness, when we talk about the completeness of, textual description, okay, the two important questions raises here. The first very important question is how to enforce the concept of comprehensiveness within the vision language model. To fine-tune CLIP, to fine-tune PLIP, or to fine-tune any, MI0 model, you have to enforce the concept of comprehensiveness. So this is the first question. Why? Because we do not have a ground truth data. The expert pathologists haven't, annotated, haven't, given any textual description for any kind of, histology images. The second question arises how to formulate a new contrastive pre-training loss function. So if we can answer the first question, which is similar to, introducing elephant in the room, the second question is still straightforward, just putting ice on the cake. So to answer the first question, okay, what we have proposed here, a unsupervised generation of textual descriptions and visual descriptions by utilizing the existing vision language model and generic large language model. We are asking the existing vision language model and we are asking the large language model to provide the detailed descriptions of the histology images, okay, as well as produce a similar kind of pathology images. This can be done using any state-of-the-art method. Till now, PLIP and MI0 have shown a very strong generalization capability. So we have used these two models to come up with a generation of our textual description. The large language models such as GPT, which is used to get the improved textual descriptions of our of the pathology images. Here is our proposal. In our proposal, there are two important modules. The first one is the construction of a bag of comprehensive textual description one is the construction of a bag of a visual concept. The first module is more towards, getting or gathering the textual descriptions for existing pathology model as well as, the large language model, while the second one is more contributed towards generating the similar kind of pathology images using the existing VLM model. So this is the systematic illustration of our CPLIP model. In the later slide, I would like to go for how can we enforce the concept of completeness or comprehensiveness. So to run the fine tuning or to fine tune any vision language model, we need a kind of prompts specific dictionary, which is more related to pathology prompts dictionary. Why we need that? Because we do not have a ground truth textual description from expert pathologists. So we want to start our algorithm by first proposing a pathology prompt specific dictionary, and we have collected some commonly used terms used by the expert pathologists from online cancer glossaries such as LabLI and American Cancer Society. These are, a couple of, the commonly used terms used by the pathologist in our pathology prompts dictionary, such as, adenocarcinoma, lung cancer lung cancer, cervical cancer, colitis, diffuse histologic lymphoma, and couple of more. So we collected around about 500 pathology prompts dictionary here, and then top of that we further clean it, which I would like to show in the ablation study. Fine, once you have the pathology prompts dictionary, then the idea here is basically align your any textual prompt with the given input histology image. So here is the unlabeled histology instance, okay, and a predefined pathology dictionary we have, which consists of 500 textual histology prompts such as invasive ductal carcinoma of the breast, squamous cell carcinoma, lung adenocarcinoma, and so on. So the first step here is to match any unlabeled histology image with any of the keyword in your dictionary. For example, we have which can be computed using the cosine similarity by utilizing any existing vision language model, such as MI0 we have employed here. So if we connect this unlabeled histology image with any of the word in our predefined pathology dictionary, you can see that squamous cell carcinoma is the best match word here. So this histology image, seems to us like it is more about squamous cell carcinoma. So this can be done easily using the cosine similarity, and here we did the MI0. We employed the MI0 algorithm. The vision encoder and textual encoder of this method is used. The both embeddings are computed and then matched using the cosine similarity. That is one of the second step in our algorithm. So that so the squamous cell carcinoma is the best match word, which would like to extend it to fill the concept of comprehensiveness here. Fine. We asked GPT, okay, the large language model, the following query now: generate 5 phrases to describe the squamous cell carcinoma. So here the GPT-3 is pulling out a couple of description. For instance, the squamous cell carcinoma is a type of skin cancer that originates in the skin, flat squamous cells in the top layer of the skin. So 5 similar kind of textual description GPT has pulled out for us when we ask the query from the GPT that generate 5 different phrases to describe the squamous cell carcinoma. We further asked from the large language model to provide some major causes, also the major symptoms for the best match word, which is a squamous cell carcinoma. So here is the result pulled out by the GPT-3. So one of the major causes of squamous cell carcinoma is ultraviolet radiation exposure, pre-existing skin damage, and conditions like actinic keratosis. Couple of major symptoms here are skin changes. One of the most commonly early symptom of squamous cell carcinoma is the development of an abnormal skin lesion and persistent sore or wound in the skin. So GPT-3 did a very nice job. It pulled out the 5 different textual description for the best match word squamous cell carcinoma. 3 major causes. Of course, we can extend towards more causes and more symptoms. So altogether, we got 5 textual description, 3 major causes, and top of that, 3 major symptoms for the best match word squamous cell carcinoma. We further asked the CPLIP text encoder, which is the existing vision language model, to give the textual description if we feed any unlabeled histology instance. So here, The idea works like that. Given the text encoder of the PLIP model, we feed image encoder, we feed image to the image encoder, and then we find the matching of the visual, we match the visual embedding with any of the textual embedding. So here, the PLIP text encoder pull out 5 or 6 different descriptions of the unlabeled histology image. So here in step C, you can see that this is the image to text description, while the rest of other is only text to text matching from the GPT. Squamous cell carcinoma of the external auditory canal and temporally bone, this nodular and cystic hydradenomas is perfect. So these are a couple of descriptions we pulled out using the existing VL model like a PLIP model. Fine, all together, okay, we can then put in a bag. So the bag here contains 21 different types of description. The first word in the bag of textual descriptions, we are putting here the squamous cell carcinoma, then followed by the 5 textual description, 3, major symptom, 3 major causes, and 5, textual descriptions pulling out from the PLIP text encoder. So this is one of our, strong backbone of our, fine tuning the already existing VL model, which is a bag of textual description, and it is, represented by BIT. Fine. If we want to further, enforce the bag of comprehensive visual concept, okay, we can generate the similar pathology images for the best match from squamous cell carcinoma, which is text to image matching, text to text matching, and image to image matching. So here, the first step is we are asking the PLIP image encoder, okay, to give us the best match images related to the squamous cell carcinoma. So we feed the squamous cell carcinoma embedding to the textual encoder of the PLIP, and then the image embeddings are matched. So the top 5 results for the squamous cell carcinoma we pulled out using the PLIP image encoder are in front of you. So you can see that these images, the embeddings of the visual embeddings of these images, okay, matches perfectly with the embeddings of the best match word squamous cell carcinoma. In the second step, we further ask our PLIP image encoder to pull out, okay, the best match image for each textual description, which we recently pulled out by using the knowledge from the LLM. For example, squamous cell carcinoma is a type of skin cancer that originates in the thin flat squamous cell in the top layer of the skin. We feed this textual description to the PLIP text encoder. We computed the embedding, and then that embedding is then matched with the PLIP image encoder kind of embedding. So here you can see that a couple of best match images for each textual description is pulled out using the PLIP encoder. Finally, we further ask PLIP image encoder to do a job for us as a image to image retrieval. So unlabeled histology instances, feed it to the PLIP image encoder, and then PLIP image encoder computed the embedding for you. The embedding is then matched with already existing data set, and here are the top 5 best match images, which we just pulled out using the PLIP image encoder. Fine. All this together make, another bag, which is known as a bag of a visual concept. So here you can see that this bag contains 21 different histology images, which perfectly matches with your unlabeled histology image, unlabeled histology instance. So you have a one bag which contains, bag of text. You have another bag basically which contains a bag of visual concept. So the second question to answer here is how to align, multiple instances with the multiple textual descriptions. So the idea here is quite straightforward. In the existing vision language model, you are basically aligning one-to-one align. You are basically doing one-to-one alignment, and the contrastive loss function is straightforward. Here we are basically making 2 further loops. 2 more sums are, injected in the traditional pre-trained contrastive loss function. Here, the idea here is within each bag, okay, look at each image, and within each textual bag, look at each textual description. So if you found any of the positive pair, okay, that will be drawn closer to each other, while the divergent pair will be distance apart. So this basically pre-training many-to-many loss function is trained on top of the ARC data set. We start our algorithm, we start the fine-tuning of our algorithms using the baseline data set known as ARC, which is basically one of the similar work from tissue image analytics lab. On top of that, we generated the textual description as well as the visual description from the ARC dataset. So altogether, we, pre-train our model on almost 200,000 images with the varying kind of a textual description. Similar to the PLIP and MI0 model, we use a similar zero-shot evaluation, giving the pathology images and their input class prompts. We ask text encoder and image encoder which image belongs to which class. So here you can see we computed the image embedding from our CPLIP model. We further computed the text embedding from our CPLIP model, and here the classifier works like that, similar to the PLIP and MI0. Fine. So in the results section, we have done couple of very good experiments. The first one is based on tile-based zero-shot classification. The data sets we use are, 5 different data sets we use. CRC 100K, which is a colorectal cancer data set containing 9 distinct labels. DW-SSS4 LOAD, which basically contains a lung adenocarcinoma cancer data set for classification of tumor versus normal. The pan-nuke data set, which is more diverse nuclear segmentation and classification data set coming up from the TIA lab. And similar to the PLIP, we did the patch classification using the 2-class label tumor versus normal, followed by digest part data set, which is a colon cancer data set, and CyCap prostate cancer data set for Gleason scoring with 4 label. Fine. The WSI level zero-shot classification has also been performed, which is a kind of a similar mill-based classifier. You have to inject in top of your textual encoder and the visual encoder. So we injected both of these encoders to estimate the embeddings for our WSI classification task. So here you can see that we then perform top K pooled scores per class, and at the end the slide level prediction is then evaluated. Fine. For the WSI based zero-shot classification, we use 4 publicly available data set containing Chameleon 16, which is a breast cancer data set for lymph node metastasis detection. The TCGA BRCA data set, which is invasive breast carcinoma data set with 2-class label, invasive ductal carcinoma versus invasive lobar carcinoma, and TCJ RCC, which is basically a kidney data set containing 3 different class labels, and TCJ NSLC data set containing non-small cell lung cancer with 2 classes, lung adenocarcinoma and lung small cell carcinoma. Fine. For the segmentation, we did a similar setting as proposed in the MI0. We estimated the label of each patch and computed the performance. So that each patch is then labeled as the segmented or the label of the cancer is given. So digest path here, colon cancer data set with 2 classes, 2-class label tumor versus normal, and CyCap data set containing 4 different labels of the class. So we did for the normal versus cancer only. For prostate cancer and Gleason scoring. Here is the performance pulled out by our CPLIP algorithm. You can say that the weighted average F-Meyer score is computed for different data set, and you can see that CPLIP is basically improving almost 10 to 12% performance compared to the existing vision language models such as PLIP, MI0, and BioMedClip. More specifically, you can see the tile-based classification performance on CRC, 100K digest path, CyCap, WSSS4 LOAD, and pan-nuke dataset, where you can see that we have shown very strong generalization, zero-shot capabilities of our CPLIP model compared to the Kunz, MI0, and PLIP model. The second table is more about WSI level zero-shot classification, where different image encoder, text encoders are used, and you can see that strong generalization performance as evaluated on Chameleon 16 TCGA dataset. Almost 8 to 10% performance is improved compared to the existing vision language model. If you would like to further explore the zero-shot segmentation capabilities of CPLIP algorithm, as I discussed before, the patches are extracted from the whole slide images. Then each patch is labeled as a normal or the cancer. So here you can see that CyCap and digest part data sets are utilized, and you can see a very strong, segmentation capabilities of our CPLIP model compared to the MI0, Kunz, and PLIP model in the literature. We conducted a couple of ablation study as well. A couple of questions raises which heterogeneous resource is suitable for gathering comprehensive visual textual description in the pre-training CPLIP model. So here you can see that we conducted 5 different kind of experiment. In the first experiment, we collected a 500 words from the online cancer groceries. Then on top of that, the 500 words, we asked GPT to extend those, 500 words. And then on top of that, the PLIP model is used to extract the textual description. So you can see that the performance is varying across different data sets. Then we further clean our dictionary. Okay, out of 500, 300 words we have, ignored, and only 200, histology specific prompts are considered on top of GPT-3 and the PLIP. And you can see that the performance is then improved compared to the unclean version of our dictionary. Then only one can say that, okay, fine, we have a dictionary of 200 only word. Why not apply the zero shot classification here, to align your astrology images with the dictionary? So you can see that the performance is not that much, attractive compared to the proposed algorithm. Then we further, deleted the PLIP model textual description, and we asked our model to train on D200 plus the GPT-3 description, and you can see that the performance was not that much good as compared to the performance when we, consider the ground truth, the GPT-3 and the PLIP description. So the ground truth textual descriptions are coming from the ARC data set, while our unsupervised proposal is the second ablation study, which is almost 2 or 3% downgrading the performance compared to the ground truth evaluation. It means that the heterogeneous textual resources are somehow good compared to the ground truth data. But of course, 100% we cannot rely on the unsupervised learning paradigm here, what we have proposed. Fine. One can ask which bag is more important, the textual bag or the visual bag. So the bag of comprehensive textual description is more good, or the bag of comprehensive, visual concept is more good. So we conducted 2 more ablation studies here, where we have trained our algorithm by aligning only one image for the textual bag. And you can see that the performance is again fluctuating across different data set, as well as if we apply only the visual bag, the performance is again, a bit low compared to only enforcing the textual bag. While we enforce the both bags simultaneously, this is a proposed algorithm, and the performance always, gets better if you are enforcing the bag of comprehensiveness in terms of, textual description as well as in terms of, visual concept. Fine. So here is the ablation study, while we use different, while using different vision encoder and textual encoder, because some of the encoders are, in domain, such as, PLIP, the GPT, and the vision transformer base with a batch size of 32. And here is, some of our, textual discoder, which are really, out of domain, such as C transport, which is basically in domain histology vision encoder, while bioclinical word is, again, out of domain, large language model here. The vision encoder, I mean. So here you can see that the best performance we pulled out using the CPLIP with out of domain encoder using C transport and bioclinical word. Nowadays we have more, a foundational model, so anyone can use any of the vision encoder and language encoder here to further, boost the performance. So we have done this ablation study just to, give a message to the community that the performance may reflect if you are using different kind of, vision encoder and the textual encoder. So in conclusion, we propose a CPLIP, which is an unsupervised learning paradigm for generating textual description and visual concept. And this is the first time, this is the first of our attempt in the computational pathology task. We gathered the, data from different or heterogeneous sources. CPLIP demonstrated impressive performance improvement across various, data set across various computational pathology applications. And it has, made a new kind of benchmark across, PLIP and the MI0 methods. Of course, I would say CPLIP is still a unique method that does not rely on, training large scale ground truth data set, and it also improved the zero shot generalization capability. Couple of, take home messages are here for the CPath community. Vision language models in computational pathology will almost replace the vision only models due to their impressive zero shot capabilities. This is one of, our take home message I would like to give to the computational pathology community, because all models or all development are going toward the vision language modeling in computer vision. And you will see in the next decade, or maybe in the upcoming 3 to 5 years, that vision language modeling will replace the vision-based foundation models only. Fine-tuning VL models with less number of parameters in CPath is one of the great interests in the computer vision community. So if someone is going to, propose another, million images data set and align million images with, textual description, I don't think so we can further push the performance. The next kind of, ocean for us is to work on fine-tuning a vision language model. We don't need data. We only need a kind of, new scientific algorithm which we can fine-tune for the vision language modeling. Well, the next era will contribute more towards the development of cancer GPT. We want to deploy, a GPTs, a pathology GPT in the clinical setting, which pathologists can, interact with the GPT model and can ask the basic questions and get their answers from the cancer GPTs. So to accomplish this task, what we need to achieve those objectives, we need high-level textual description from expert pathologists to 10 LLM. The problem is, should we trust on these large language models or not? Not. This is again, a kind of a cloudy question we have, a kind of a black box. So in order to trust that, we need to involve expert pathologists to give us a high-level textual descriptions. Well, ARC is one of the possible attempt, but again, ARC dataset is a very small kind of dataset. So the next option is we have a fine tuning. Well, I understand this is a tedious job, but we have to do that in order to test our AI model in the clinical practice. Thank you very much. And I hope that it was a good talk. Stay tuned. CPLIP ++ model will be out very, very soon, hopefully in the upcoming 2 weeks. Thank you very much.
Brilliant. Thank you, Sajid, for a really interesting talk. Sorry about that. We had some technical difficulties towards the end, but don't worry, we heard all your talk. So yeah, with that, shall we open the floor to questions? So does anyone have any questions they'd like to kick us off with? Sorry.
These two online.
It's
frozen.
I think it might just be on Mark's laptop that Sajid's frozen. You can go on, sorry. Brilliant. So yeah, do you have any questions, sorry, in the room? Start us off with. I suppose I had a comment really on one of the final slides that you presented about the take-home messages and about vision language models almost always replacing vision only models. I wonder if you go into a bit more detail at this. So I suppose in niche cases this will not necessarily will be difficult.
Fine. It is, fine.
What was my question?
Well, it is difficult to beat the vision only models, okay? But if you look at, the capability of Kunj, the capability of,
Hello. Hello.
Yeah, can you hear me?
Yes, I can hear you. Okay, can everyone? I think it's just might be just for your laptop, Mark, that's not seeing it.
Yeah, it's on my screen. It's just not.
Okay, brilliant.
So the question here, the vision only model, okay,
Yeah.
will be preferable in the future compared to vision language model or not? Okay, fine. If you look at the, generalization capability of uni model, okay, and the generalization capability of CPLIP model and Kunj model, you will see the vision language models are, booming, okay, in the upcoming months, and they have, almost beaten all the vision only models. So, and a lot of development is going on for, enhancing or improving the vision language model compared to the vision only models. So I think I would say that in the future, okay, the computer vision with only vision level capabilities, okay, by ignoring the textual description or text kind of capability will not work very well compared to the these video GPTs are there, these kind of path chat is now here in front of us where you can see the impressive performance, impressive capabilities of language as well as the images as well. Yeah.
Thanks, Sajid. So we've also got a question on chat from Anihil, who said, "Hey Sajid, thanks for a great talk. Is the fine-tuning / training code available for CPLIP?"
So as I mentioned, our CPLIP ++ model will be out soon, and we have released the pre-trained models of our CPLIP model. We are still in the process of, releasing our training source code with the, releasing the CPLIP ++ model very soon. Yeah.
Brilliant, thank you. And I suppose also a question about one of the final slides again about the comparisons with the different encoders. So
Yeah.
why do you think that C-trans path appeared to get the best results in terms of vision encoder?
Mm-hmm. So the reason behind that is, the C-trans path is trained on a large scale, TCGA cohort, the histology data set. And this is one of the reasons that the C-trans path has already been trained on, a pathology or histology kind of, data. That's why this is one of the reasons. While if you look at, the PLIP model, the PLIP model is also trained on histology data set, but it is trained on a very small scale data set compared to the C-trans path. This is one of the possible, reason behind why the CPLIP model works very well while using the C-trans path and bioclinical work.
Okay, so it's the scale of the training data.
Yeah. But if you look at the performance variation, okay, the performance improvement is not that much, compared to the out of domain CLIP model, which is trained on, the ImageNet. So if you can see that whenever we are, utilizing the vision encoder, which is trained on histology data, so you will see a very nice performance compared to the CLIP model only.
Okay, brilliant.
Yeah.
So does anyone in the room or online have any questions they'd like to ask?
Yes, I have a quick one. You said the CPLIP ++ is on its way. So what does the ++ mean? What are you planning to add?
So I'm not. Did you hear that question? Sorry, Sajid. So
I couldn't. There is a lot of.
Oh, sorry. So Mark said that he sees that CPLIP ++ is now will be available soon. What is the ++? What's the addition to the model?
Well, we have shown some fine. Good question. You will see within 2 weeks. But I can explain here what we are going to, add in the CPLIP ++. We are getting textual description from more, a strong model, such as, the path chat, okay. As well as, we are trying to, extend C++ for fine tuning or linear probing kind of result. On top of that, we have trained the CPLIP ++ model on a very large scale data, which is a TCGA data set, and we have utilized almost 60 to 70,000 slides.
Fantastic.
Yeah.
And this will be out in about 2 weeks. Brilliant. So if we don't have any more questions in person or online, I think I'll finish with one final question. And I know you've already given some of your thoughts already towards the future of foundation models in computational pathology. But yeah, just to finish, can you summarize really what you think is going to happen over the next 12 months in computational pathology and how foundation models are going to, and these language vision models are going to really revolutionize computational pathology further?
Well, as I mentioned that two very good take-home messages from this work is, one is, of course, vision language model will replace the vision only model. And this is what we have, put the argument here. Okay. Why? Because these models are booming day by day, and they are, providing a very nice performance. The second, instead of proposing a very large scale, kind of vision language model, the challenge is, their deployment challenge in the clinical practice. Okay. So instead of, proposing more larger data set, instead of, proposing more large scale vision language model for histopathology, why not we propose some methodology to fine tune, already existing methods to further, push the performance towards what pathologists are, expecting. Fine. Hope so it makes sense, yeah?
No, it does, yeah. So thank you. Well, yeah, if we've got any more questions, I suppose we'll call the seminar to a close. But thank you very much, Sajid, for a really, really interesting talk. And it's been great to have you, visit the TIA Centre virtually again. And best of luck with.
Yeah, I might be attending BMVC
Okay.
early December. So hope so. I will interact with Dr. Nasser and would like to visit TIA Centre someday. Yeah,
Yeah, definitely. Nasir's just commented to say congratulations on the good work and he hopes to see you soon.
Thank you.
And yeah, just like to thank everyone for attending, both online and in person. This is our last planned seminar of the academic year, and we're back with our seminars in the autumn. We're kicking off with Max Liu on PathChat,
Yeah.
and we've also got invited people coming in and visited in person, such as Dr. Danielle Belgrave from GSK and Jack Breen from Leeds, and we've got lots of people lined up. So thanks again, Sajid, for a really, really great tour,
Welcome.
and thanks
Thank you.
everyone.
Thank you.